Hello everyone, Professor Dustin here. In this video, I'm going to give you a brief overview of vector calculus. So those are two words that we have some connection with and we understand. A vector, that's an arrow with a magnitude and a direction. We use it to represent position, velocity, acceleration, forces, things that have directions. And calculus, right, that's a branch of mathematics that deals with continuously changing functions. So if we need to understand something about how functions change, typically we need to use calculus. So the combination of these two words might seem kind of scary, but actually there's not a lot here that we need to know. We just need to be familiar with notation and be able to do a few simple manipulations. So I'm going to start by writing a vector, probably the vector you are most familiar with, and that is the position vector. So I'm going to write it as R, and then I'm going to write it in unit vector notation. So that's x hat. So that means whatever the position of the object is along the x direction is x, and that x hat tells me along the x direction. Y hat plus z hat. So as coordinates, this vector has the coordinates of the end of the arrow is x, y, z. But this is just a position vector relative to some origin. So what we need to do, we need to know how to take derivatives of a vector. So specifically, the velocity vector, the definition of the velocity vector is the derivative of the position with respect to time. But now we have a position vector which has three components which each have unit vectors in them. So we need to know how to deal with that. Fortunately, it's actually very easy to deal with that. So I can just put my definition of dr of r into that position right there. X hat plus y hat plus z hat. And I can proceed to take the derivative through that position vector. This is a sum of three terms, so the derivative will hit each term individually. So if I want to write that all out, it looks something like this. And now I can take the derivative of each one of those terms. Let's first focus on this first term, because as you can probably guess, each term is going to be very similar. So my derivative, I'm going to need to do a product rule, right? Because there's two pieces here. So I'm going to need to hit that guy and then hit that guy. But actually, we can make this much simpler. Although the position of an object might be changing as a function of time, the x position of an object, the unit vector is always pointed along the x direction and always has length 1. It always has a magnitude 1. It never changes in time. So x hat is independent of dt. And we simply get dx dt times x hat, because the time derivative of x hat is 0. It's constant. So we just get that. So now I could just rewrite this, this vector using this answer pretty simply. So that's just the derivative of x dt, x hat, dy dt, y hat, plus dz dt, z hat. Each one of the things in front of the unit vectors is the component of the velocity in the x direction, the component of the velocity in the y direction, and the component of the velocity in the z direction. Very simple. Okay, great. So that's just how you take derivatives of a vector. You just carry the derivative through each term. Don't do anything to the unit vector because those are constant. And then we can also finally write this as vx x hat, vy y hat, plus bz z hat. Okay, so that's how to take a derivative of a vector. The last vector we might be interested in doing this on is the acceleration. So let's just do that. So I've copied my answer right there, and now I want to calculate the acceleration vector, which is by definition just the derivative of the velocity with respect to time. I have the velocity vector right there, so I'm just going to put that right into there. like that. And now I can just hit each one of these terms with the derivative with respect to t. I shouldn't have to go through this again. The derivative hits this guy separately from this guy, separately from this guy, and since x hat is still constant in time, the derivative of x hat is 0. So this term, you just get the derivative of the velocity with respect to time in the first position, velocity with respect to time of the y component of velocity there, and with respect to time, the derivative of the z component of velocity there. And again, I can write this as the acceleration in the x direction times x hat plus the acceleration in the y direction times y hat plus the acceleration in the z direction times z hat. Because I can write any vector like that. The component in front of the x hat is the component in the x direction. Okay, great, thank you. So this has basically been how do we need to use vector calculus in a physics class. Typically, this is what we need to do. We need to know how to take derivatives of vectors. Fortunately, it's really quite simple. If the function here in front of the x hat, in front of the y hat, gets more complicated, then you might have a harder derivative to deal with. But the addition of vectors into our consideration should not be too complicated. Just break up each component. Remember that x hat, y hat, z hat are constant in time, and just take the derivatives. Okay, great. Thank you for watching. I will see you in class.